Hello, everyone. Welcome back. So we'll continue our deep dive into deep neural networks, just to put a mouthful of words. So we are exploring now mechanisms to allow us to train us effectively deep neural networks in a stable manner and without overfitting. So we have seen so far that it's useful to have deep neural networks. That training deep neural networks is, however, difficult. We have seen some solutions to address vanishing gradient via the ReLU, the rectified linear units activation, which replaced what was the standard at that time, sigmoid and tan-H activations. And we have seen also the mechanisms for doing weight regularization, which is L2 regularization of weight decay. We'll go now to explore some strategies which are specific to neural network architectures, and the first one will be dropout. But before that, let me outline you a bit the specifics of deep neural networks and deep neural network regularization. So if you remember our Pokemon slides, deep neural networks are some big beasts, right? With many parameters, way more parameters than data, 180 more. But in this case of a wide ResNet, trained on or on ImageNet or on CFAR, I don't remember exactly. You had at 180 more times more parameters than images, and this is quite common to happen. Right, so we cannot. I mean, while some of the regularization strategies that we had before are working to some extent, we still need to find some strategies that are specific to these big deep neural networks. So if we take a look at most of the neural networks, at least by the way they were until a few years ago. So I have here an example, a classical example of the LeNet5 architecture. In general, these architectures follow the same structure. You have a stream of a sequence of 5 convolutional blocks, and then you have a few fully connected layers that are dealing with the classification, with the semantic information. So we say that usually the convolutional blocks deal with the feature extraction and learning information, learning and extraction. In the fully connected layers that are at the end, they are dealing with the classification. And in general, most of the weights are concentrated here in the final part of the network. So I'll take an example of a more recent neural network. Let's take VGG16. So again, it has 5 convolutional blocks, 1, 2, 3, 4, 5, and then we have 3 fully connected layers. And I'll use another visualization to help you understand a bit better the distribution of the weights. So here we have the input, and I'm displaying for each convolution layer the size of the activation maps and the number of parameters. So we do like that until we get to the final fully connected layer. Since it's an ImageNet trained model, we have 1,000 output decisions because we have 1,000 classes in ImageNet. So what we can see here is that in the first layers, we have very few parameters, right? We have just some filters practically. So we have 36,000 here parameters, while we have big activation maps. So we are still at the beginning of the network, so the images are bigger. So the activation maps are still also big. So this occupy quite a bit of space on the GPU. When we go a bit down, so when we go towards the end of the network at the at the fully connected layer, so we see here when we transition from convolutional layers to fully connected layers, there's a huge pile of parameters, right? So here we have we can see that we have 7 by 7 by 7 512. So this is the size of the feature map here, multiplied by 4,000, which is the number of neurons at my current layer. So this all at once, I have 100 million parameters. Moving on to the next layer with again 4,000 neurons, I have 16 million parameters. And then at the final one, I have 4 million parameters, which is a lot compared to all the convolutional the parameters in the convolutional layer. So as I was saying, we have here most of the weights, at least in these standard architectures, were concentrated in the final part of the network. So this is where dropout enters, right? Because we must find the mechanisms to not allow these numerous parameters in the final network overfit, in the final layers of the network overfit. So this is what Dropout addresses. So Dropout is among the first, well, I think it's the first deep regularization technique. And the principle is quite simple. So here I have a normal neural network, fully connected layer with everybody connected to everyone. So what we do in Dropout, we simply deactivate, remove some units at random during test time and during forward. Right. So here, I just ignore the output of this deep neuron here. Again, I ignore the output of this neuron here, and so forth. So, and then when I do another forward, I do a different random selection of the neurons. So at any point so at different points in the forward, during training, iterations during training, I will have different combinations of neurons that are learning to interact. So and once I do that at test time, I come back to the regular setting, right? So I still use all the neurons. So the intuition here is to reduce the network dependency to individual neurons and to distribute the representation. And this allows to create a more redundant representation of the data across the neurons. To some extent, it's similar to what teachers do usually with when making teams of students. I mean, when making teams of students, trying to all the time randomize people, not to always have the same pairs of students, because you might have in one team a student that is always the one that works, and the other ones, since are used to him or her to work, they just step aside. And if they do that across the projects, those two students will never learn. So the whole interest is to randomize teams of students across projects so that everyone will be in different contexts, and they will eventually learn and come up with end up with something useful out of the course. So this is actually also the intuition behind Dropout, to not allow just one individual neuron to fire to a certain image and such that you can recognize. If you remember, as I was saying, since you have so many neurons compared to images, you can have just actually really a neuron that fires only when that image that it learned to recognize is present, and this will allow you to have a very reduced training loss and to finish training. But this is actually overfitting. So that's what we try to address here at Dropout, to not allow this behavior and to distribute the representation for each image and for all the features across the whole neuron, the entire set of neurons in our network. So in Dropout, we also have this ensemble interpretation. Since at each time we do a forward with different subsets of neurons, we can think that we can have as an ensemble of multiple sub networks like that. That are masked. So when we say masking, it's selecting which neurons to deactivate or to keep alive. So if we imagine that during training we train this ensemble of networks, at this time it's actually since we use all neurons, is as if I averaged all these ensembles to make a prediction on my data point. So this is to go into more details into what how Dropout works. So we have to decide on which units to use Dropout and with what probability p the units are dropped. Well, the first part is easy. We usually select fully connected layers, although there's variants also for convolutional layers, but in general it's applied principally on fully connected layers. And then, we have to decide of the probability. Usually 0.5, but then it depends on the architecture. But you can start safely with 0.5. So then, during training for each sample, we have as many Bernoulli variables as units, and we sample them independently to select which units to keep and which to deactivate. Right? That's it's in a nutshell. That's what it. So we just during forward for each neuron we sample from this Bernoulli. We give a trial, and it should be output as 0 or 1, and this allows us to decide whether we activate or deactivate the neuron. There's a trick here because we have to keep, since we have different, because we risk having different behaviors during during training and during testing, because if a neuron is removed, we practically replace its output with zeros. So we say that it doesn't do anything, we have zeros. But if we do like what's custom in Dropout, we have like 50% of the neurons deactivated. This means that we have an increased sparsity. Because we'll have half of the feature maps, or up to half of the feature maps, to be completely zero. And at test time, we used all the neurons, so we will not have all the feature maps. So we'll have just very few feature maps with zero, or if not any. So we need to make sure that these two behaviors are compatible between training and testing. So in the initial paper, what the authors did, and it's in this figure here. So to keep the means of the inputs of the two layers unchanged, the initial version of Dropout was multiplying activations P during test. So we practically multiply here by 0.5, for instance. So we multiply all the activations by 0.5, such that you will have a certain to keep more or less the same statistics. But what's currently more used and more standard is what we call the inverted dropout. So we multiply the activations by 1 divided by 1 minus p during training, and at test time we do not touch at all the network. I'll show you this in a moment with some code. But before that, let's see how actually it impacts training. So we have here an example where an MLP with 3 hidden layers is trained on MNIST, and we have here installed the training loss, which goes very nice to 0. But then the validation one, it goes. We can see here this pathological behavior of overfitting. So we have this big divergence compared to the training loss. So this network doesn't lose any dropout. If we add a dropout with a probability of dropout of 0.2, we can see that there's significant improvement. So already my training loss doesn't go as fast as to 0 as before. And the validation loss is very close to the training one, right? So we don't have this big gap in between these two. So I'm more confident that my network will do a better job in the validation and in the test set, because it doesn't just memorize the values in the train set. So well, with dropout, of course, since we have this hyperparameter of the dropout probability, we have to be careful. If we have too much dropout, for example, here is 0.8, we drop 80% of the neurons at each time. It's not helpful at all. So this network doesn't learn anything. So we have to be mindful on what the probability dropout probability to set. As I said, 0.5 for big networks is quite a reasonable choice. So in this experiment from the original dropout paper, the authors show across several architectures with 2 to 4 hidden layers and with 1,000 to 2,000 hidden units or neurons, we can see the difference in the classification error without dropout and with dropout. So this is the classification error on the test, right? So we see that it's a lot better when we have dropout compared with without dropout. So it's consistent across all types of architectures and sizes of architectures. So to see how it works in PyTorch, we'll have an example where we apply a dropout on a tensor. Well, in practice, it will be also applied on a tensor of weights or activation. Sorry. So we can see here that I have X. It's a tensor which is full of ones, and I define here a dropout layer with probability of dropping out 0.75. When I pass my X through dropout, I get this result Y, and we can see that I have mostly zeros. This is their dropout, and here I have some values which are 4, right? So instead of 1. So if you remember, I was telling you that during train time we multiplied the remaining activations by 1 divided by 1 minus p. So 1 minus p is 1 minus 0.75, which is 0.25, and 1 divided by 0.25 is 4. Right. So that's why we have all these values here with 4, and the remaining ones, the masked ones, are 0. Well, if we simulate here a loss and we do a backward, we can see that in the gradient we have a gradient coming also only from via the activations that have been kept. On the 0 ones we have no gradient passing by, so this means that the neuron behind it is completely off the loop from this forward and backward cycle. So how do we use these dropout layers? So as I said, usually the most common is to have them with linear or fully connected layers, and usually we just add them after. So we have our starting network, and here we just see that we can add 2 dropout layers like this in our sequential, and it works as it is. We have to pay attention to when using the dropout into a model to see in which mode it is, whether it's in train or test mode, because the dropout has, as you've seen, it has different ways of working when it's in train mode and in test mode. So I'm defining here how it behaves. So I have here a dropout layer and then a dropout. I added to this sequential model, and I consider that my dropout is in I verify if my dropout is in training mode. This is true, and I set my my model into false mode. So this well, either I use train of false, either I use a model.test and to know that the model is in test mode, and we can see that that this also applies to the subsequent layers in the network. So whenever I set my model to train or to test, it will automatically put the specific layers that I have into train or test mode. So just to see the differences between a model when using dropout in train mode and in test mode. So here I have the same example: a dropout layer, a model that has a dropout layer inside, and an input tensor. I set my model into train mode, and I look at the output of my model 2 times. And so you can see that my outputs are different each time. So my network is not deterministic because it's in train mode, and dropout applies different random masks to mask out different neurons each time. So this leads normally to different results. This is coming sometimes scary for newcomers when they have this and they notice this behavior that the network gives different outputs each time. But usually, yeah, that's the first thing to look for, whether we have layers that have different behavior and train time and test time, and if the network is in train mode or in test mode. So when I put the network in evaluation mode, in test mode, we can see that when I pass my my input tensor 2 times, I get the same output because now my network has a deterministic functioning. As I said, dropout was initially introduced in particular for fully connected layers because it's there that we have the large chunk of weights. And by the way, its design, it's a bit less compatible with convolutional layers. What's a common because what's a common practice is to drop channels instead of when we were using it in convolutional layers. We name it differently. We call it spatial dropout, and the behavior is a bit different. We drop channels instead of on the individual units. So the challenge here is that the units in a 2D activation map are generally locally correlated, so we cannot just activate just a weight, because dropout will have virtually no effect. So what we do, we drop channels instead of individual units. So we have here an example in PyTorch. It's called dropout 2D, differently from a normal dropout that we have in a fully connected layers. And we can see here we have a tensor with 4 dimensions, which is all ones. And we pass it through, and we can see that we have some feature maps which are completely 0. So here by default, the probability of dropping out is 0.5. So it practically just it puts to 0 of a feature map, erasing the output of a filter. There are some new variants of dropout. The most powerful one is drop block. So instead, as I said, instead of just dropping some random pixels in the feature maps, which are not very helpful, what they do here, they drop blocks of a pixel at a time. So they take consistent blocks of pixels that are dropped out. So this forces the network to look also to learn from the other informations. So here with green, it's actually the contour of the dog, which is called the useful information, right? So if I mask the head of the dog and part of the legs, the network will have to recognize the dog also by other features, right? By the fur, not just by the mouth, the nose, and ears. Sorry. So this is actually quite a nice way of doing dropout, and it makes sense, and it works quite well in practice. There's another variant of dropout, which was actually proposed by the same authors in the original paper. It's called the Gaussian dropout. So what they do is to generalize Bernoulli sampling over neurons to sampling from other distributions. So instead of just having a Bernoulli over the weight to decide whether it's 0 or 1, what we do here, we practically decide to perturb the feature maps by a random variable. So we just take a random variable from either from a normal distribution center in 0 and with variance 1, and we add it to the feature map. Either we sample it from a distribution centered on 1, and in this case we just add it. We consider it as multiplicative noise on the feature maps, and this has been shown that it's actually working equivalently with the original dropout, the drops activations. However, it's a bit more longer to train, and it adds a bit of an overhead by this weight perturbation, not weight perturbation, activation perturbation across all the outputs. And the authors showed that they can actually generalize this sampling from a distribution on 1 and sigma square, where sigma becomes an additional hyperparameter to tune, just like the P in the starter Bernoulli. So we can learn or set what type of noise and how much perturbation you want to add to the Gaussian noise. Okay, so this was dropout, which was among the first, which is the first deep regularization technique. In the next episode, we'll continue with some newer variants that shifted the game to even to new ranges of performances, and we'll see in the next slides about batch normalization and residual networks. See you in a moment. Thank you for your attention. Bye bye.